Whole numbers, integers, they're kind of the comforting, predictable foundation of our entire mathematical universe. You add them up, you swap them around, and the logic, it remains ironclad. But what happens when we take a hammer and shatter those integers into pieces? When we enter the fractional realm of rational numbers, do those same fundamental rules still hold true? Or does the whole mathematical system just start to buckle under the pressure?
Welcome to this explainer. Today, we're basically putting rational numbers through a rigorous laboratory-grade stress test. We're going to push these fractions to their absolute limits just to see where they hold up, pinpoint exactly where they shatter, and ultimately uncover the underlying cheat codes of the universe.
Okay, let's dive right into this. Here's our roadmap for the test. First, we'll meet the numbers. Then, the closure test. Next, swapping and grouping, followed by some special tools. And finally, we'll tackle the combo move. All right, section 1. Meet the numbers, the building blocks. So before we start smashing these building blocks together, we gotta define exactly what they are. A rational number is essentially just any number you can write out as a fraction. Actually, that's exactly where the name comes from, the word ratio. It's literally just a ratio of two integers. We call this the P over Q form, right? So P is your numerator on the top and Q is your denominator on the bottom. But, and this is absolutely crucial, here is the golden rule. The denominator Q cannot be equal to 0. If you try to divide by 0, the entire definition just falls apart. Keep that rule in mind because it's going to cause some major drama in our stress tests very soon. Moving on to section 2, the closure test. Does math break? So what exactly does closure even mean? Well, think of it as a safety test. We want to see if combining two rational numbers always safely gives you another rational number back. If it does, the operation is closed. Let's look at division to see if the math breaks. Say we divide 1/2 by 1/4. If we flip that second fraction to multiply, making it 4 over 1, we get 2. And 2 is a rational number because we can just write it as 2 over 1. It passes. Easy, right? But what if we take 1/2 and try dividing it by 0? 0 is technically a rational number itself, expressed as 0 over 1. But the very second we flip it to multiply, it becomes 1 over 0. Suddenly, our denominator Q is 0. That totally defies our core definition, and the test completely fails. If we check out the final scorecard for this closure test, a pretty clear pattern emerges. If you add, subtract, or multiply two rational numbers, you will always perfectly generate another rational number. They pass with flying colors. But division? Division is our very first rule-breaking rebel. Because of that 0 loophole we just saw, division is not closed for rational numbers. And you might be wondering, why does this matter outside of a math textbook? Well, computer programmers rely on this concept of mathematical closure every single day. They have to write code to ensure their algorithms don't suddenly crash by spitting out undefined values, like those highly dangerous zero denominators. All right, section 3, swapping and grouping, the true rule followers. First up is swapping, which is formally known as the commutative property. The word commutative just comes from commute, meaning to move around. The question here is, can you move the numbers around, swap their order, and still get the exact same result? Let's stage a little battle using subtraction. On one side, 1/2 minus 1/4 gives you a positive 1/4. Pretty straightforward. But let's commute them. Let's swap them around. 1/4 minus 1/2 instantly drops you into negative territory with negative 1/4. They are definitely not equal. Subtraction completely fails the swapping test. Next, we're going to test grouping, formerly called the associative property. Following standard order of operations, we always solve the brackets first. Say we've got 1/2, 1/4, and 3/4, and we're adding them up. Let's group the last two together in a bracket. Step 1, 1/4 plus 3/4 equals 4/4, which nicely simplifies to just 1. Step 2, add that to the 1/2, waiting patiently outside the bracket, and you get 3/2. Now, what's really interesting here is that if we changed the association, if we grouped the first two numbers instead, we would still get exactly 3/2. Addition passes the grouping test flawlessly. When we zoom out and look at the scorecard for swapping and grouping, a massive recurring pattern reveals itself. Addition and multiplication, they always say yes. You can swap them, you can group them, and the answer stays perfectly true. But subtraction and division, there are constant rule breakers. No way around it. And this actually happens because addition and multiplication are the pure foundational operations of math. Subtraction and division, they're really just artificially constructed inverses. And that artificial nature is exactly why they are so fragile and shatter the rules whenever we mess with their order or their grouping. Moving right along to Section 4, Special Tools 0, 1, and the inverse. I want you to think of these 3 distinct rules as your ultimate mathematical cheat codes. First, there's the rule of 0, and hold tight because we're going to get back to that incredibly powerful tool in just a second. Next is the rule of 1, formerly known as the multiplicative identity. Multiplying any rational number by 1 simply leaves you with that exact same number. It maintains its identity. Makes sense. And third, the multiplicative inverse. This is a brilliant little shortcut that literally just means flip the fraction. If you have 1/2, its inverse is 2/1. Mastering these concepts gives you the power to navigate and solve crazy complex equations instantly without breaking a sweat. Now let's take a closer look at the undeniable power of 0. It is an absolute force of nature in mathematics. Seriously, it doesn't matter how complex, how massive, or how terrifying a rational number might look on paper. The moment you multiply it by 0, it is entirely wiped out. Gone. The answer is always just 0. To put that into perspective, this annihilating power is so absolute that many ancient civilizations genuinely feared the concept of 0. They treated it like a terrifying void, and initially, they straight up refused to even incorporate it into their math systems. All right, Section 5, the combo move, the distributive property. We have finally arrived at the ultimate boss level of rational numbers. It's time for the combo move. And this brilliantly illustrates how the distributive property flawlessly merges multiplication and addition into one single elegant formula. Basically, you take the rational number hanging out on the outside, let's call it a over b, and you distribute its multiplication to every single fraction waiting inside those addition brackets. Let's bring this whole stress test to a close by actually conquering this boss level. We'll use our trusty fractions, 1/2 on the outside and 1/4 plus 3/4 on the inside. Let's do it the slow way first. We'll take our time and solve the bracket. 1/4 plus 3/4 is 4/4, or just 1. Multiply that by the outside 1/2, and the answer is 1/2. Okay, now let's use our combo move and distribute. Multiply 1/2 by 1/4, and you get 1/8. Then multiply 1/2 by 3/4 to get 3/8. Add those together. 1/8 plus 3/8 gives us 4/8. And when you simplify 4/8, you guessed it, it's exactly 1/2. The two sides perfectly match up. The mathematical universe holds together. We've really pushed rational numbers to their absolute limits today. We've seen exactly where addition and multiplication holds incredibly strong and exactly where subtraction and division completely shatter the rules. And now you've got the ultimate cheat codes for swapping, grouping, and distributing fractions. So what does this all mean? Knowing these fundamental patterns, how are you going to use these tools to hack the universe's language and solve your next big mathematical challenge? Because remember, these properties aren't just arbitrary rules in some textbook. They're quite literally the underlying operating system of physics, engineering, and pure logic itself. Keep experimenting, keep testing the rules, and I'll catch you in the next explainer.